So we're back in chapter 7, we're in chapter 7. Remember, we're looking at the beginning of that, the evidence for a chemical reaction. There's a little thing I want to change on this. As you may or may not have noticed, I don't like how chemical reaction versus physical reaction has been described so far, because I think it can be very, very confusing. Particularly since you aren't super comfortable with what makes a formula, what makes a compound, and all of those individual pieces. Okay? So one of the big things that happened over the last few days is I got to see the final exam. And I went through the final exam, looked at some questions, and there were two questions that I had problems with. Any idea what topic was covered in those two questions? Chemical and physical changes. And I would argue both of those questions had wrong answers, or didn't even have a correct answer option. Okay? When it comes to those on the final, I will try and see what I can do to get around that. I'm not allowed to change the final, and apparently we're now far enough into the semester that the faculty don't want to change the final either. Okay? So when it comes to your exam, I will probably pull those questions from the exam and just see how you guys do with them in general anyway. Okay? The intent being I want to see what you guys interpret out of it and what your understanding of the chemical and physical reaction is. But then instead of your exam being out of 65 questions, it'll be out of 63 because I'll pull those two questions. Okay? Kind of makes sense? So, chemical and physical changes. Rules 1 and 2, according to your textbook, are looking at a formation of a gas or the formation of a solid. Ultimately, both of those are looking at the same thing. It's a change in phase. Okay? The big objection that I had with the questions in the final was what defines a change in phase? Have we seen a change in phase where it's not physical? Or sorry, not chemical? Heating up water. Evaporating, boiling water. Sorry, that's one of the other crappy words. Okay, when we boil water, we're going from a liquid to a gas. That's a change in phase. Is that a chemical change? No. Okay? So when we're looking at the change in phase, we are not including heat in our evaluation. We do not supply heat. We do not remove heat from our reaction. We mix two materials, and a change in phase happens according to those materials, not us changing that energy term. Okay? It's a bit tricky when it comes to at least the questions within the final exam. As far as what you guys see, hopefully you'll be able to pick up and see what's happening. Particularly if we looked at equations. Okay? If we saw a reaction, okay? First off, if you see a reaction, more than likely you're looking at what kind of a change? Chemical, otherwise we wouldn't show a reaction. Okay? It's not exactly true, but it's pretty close. Our picture again showed the formation of CO2. Those were the attempted bubbles. This one's showing the formation of a solid. So again, we mixed two liquids, and now all of a sudden we see this solid. Okay? So another way you could look at rules 1 and 2 is that when we mix these things, it's not a complete phase change. We get this kind of middle ground between multiple phases. Okay? Again, I don't like the phraseology with it, but that's about the best we can do. Okay? The formation of a solid is typically referred to as the formation of a precipitate, or you see the reaction precipitate. Okay? Other big changes, you're looking at a permanent color change. You got to, again, be careful that you're not looking at dilutions or an addition of colors, okay? Like blue and red food coloring. Mixed does make purple. That is a permanent color change because we can't now separate those easily, but it's not a chemical change. Okay? We didn't change any of the arrangement of atoms within that. The last big one is an energy change. We'll look at the energy change for we'll look at each of these reactions or observations for chemical reactions with each of the reaction types that we'll see in the rest of Chapter 7. So we'll identify what things are changing in each case. Okay? Oh, and then there's your release of energy. In this case, the image I think is sodium, or one of the, what's that group 1 called? Alkali metals. One of the alkali metals being dropped into water. You generate heat, and you also generate light. Both of those are forms of energy. Okay? The next big thing that we could look at is chemical reactions. And when we talked about this, remember, you're going to have to be able to translate that reaction equation up top into words, or potentially into words. And then you'll also have to be able to translate the words back into that equation. Okay? So if I was going to read out that equation, I would start off by saying solid sodium hydride is mixed with acetic acid to produce aqueous sodium acetate and hydrogen gas. Okay? You need to have that same level of fluency when referring to the individual equations. How do you pick up that fluency? Most of it is nomenclature. That's probably the hardest part. So chapter 6, keep going back through that material. Make sure that you know how to identify the name for an individual compound. Okay? It is going to come back and haunt pretty hardcore. Okay? Yes?
Remember the different molecules or whatever, acetate, carbonate, cyanide, you had to memorize?
Yes.
The final exam, does that still hold true?
Oh, good question. I'm definitely going to have to talk with the other faculty on that one. If you can send me an email to remind me, and since you've got your computer open, if you can send it now, I will go back through and check with that. The other thing that is going to be important to note is I'm pretty sure some other instructors, as you may or may not have heard, are allowing students to have cheat sheets within the exam. I'm pretty sure that's not allowed on the final. So those instructors are actually hurting their students because their students are going to get used to using cheat sheets that they can't use on the final. Okay? So we'll find out what's going on with that, both as far as cheat sheets go and what complex ions you'll need to have memorized. So should be a bit tedious to go through and find, but I'll see what I can do. Okay? Worst case, if it pops up on the exam, there's a really easy thing that you can do to solve that problem. No, raise your hand and say, this is not one of the ones you told me to memorize. And I'm like, oh crap, you're right, and I'll write it up on the board. Okay? Yes?
Like, basically memorize the same.
It's the same ones, yeah. So what I did was went through and, I don't know what those are when you're pointing to them.
I don't know what they are. Oh, no. Yeah.
So up here, the only complex ion that we could look at would be the acetate ion. So I said there were 7 complex ions that you needed to have memorized. Acetate is one of them. Yeah. Okay. As far as the rest of the names go in that formula, you should be able to name all of those on your own. There's no complex ion in there to memorize. That's the basic naming rules. And yeah, you still need to know those. Okay? The main reason this equation was included was for this last one out here. If we're going to form hydrogen gas, we have to write it as H2. Okay? And the reason we write it as H2 is because hydrogen is an element that when in its elemental state by itself, it must be bound to a second atom of hydrogen. Okay? So it is known as a diatomic molecule or a diatomic element. There are 7 of these diatomic elements. You do have to have those memorized, all 7. We talked about 2 ways to approach that. We've got hydrogen floating off on its own, and then we have kind of a 7 in that right-hand corner. So there's your 7 elements. Okay, that may not be the greatest thing, but what I got as far as that goes. The other option is the nice little fun phrase at the bottom, have no fear of ice-cold beer. First letter corresponds to the first letter of the elements that you're referring to. Okay? So that can help you memorize those. Okay? So if I talk about fluorine gas, it needs to get written as F2 with your parentheses specifying the phase, gas. Yes?
Wouldn't cold be carbon then?
So it's not perfect. The first letter corresponds to the first letter of the element that matches it. Okay, so it doesn't match the symbol, and there's really nothing we can do about that. Okay, unless you can come up with another descriptor besides cold that starts with Cl. Have no fear of ice chlorine beer, ice clear beer. Yeah, that one kind of works. We could stick with clear beer. Okay, so I personally would actually have some fear of that, but I mean, we could adjust that to ice clear beer. Okay? You still run into that same issue that you're talking about with bromine, because the symbol for bromine is Br, and we're looking at Be. Okay? What?
Ice clear.
Have no fear of ice clear bros. Bros, bras, anything that you can use to remember it is what you should use. How about that? And since other people are mentioning up front, just in case other people didn't hear that, ice clear bras, I don't know. Okay? Ultimately, you're responsible for knowing those 7 elements. Okay? Questions about any of that? Last big thing I'll address before the next slide. We look up at the equation. Okay, I started it off by saying solid sodium hydride. How do I know it was solid? Because it had the S. You need to make sure that that shows up in your equations. You must specify the phase with every molecule within your equation. Okay? If you don't know the phase, which could happen, then you're kind of stuck. Take a stab at it and see what happens. Okay? We will come up with some rules to help you determine some phases, but in most cases, you either know it or you don't. Okay? Other questions?
When we write it out in words, do we write solid before or after? Or does it not matter?
In words, I would put it out in front. I would say it's solid sodium hydride. Okay? Just because it sounds grammatically better, but that's about it. Okay. Other questions on that? Okay, go ahead and get your notes put away. And we'll start with the quiz right away. If you get any extras, look around you, see if you can pass it to somebody else.
I've never checked out mine, but like it works.
And then keep the extras on the outside. I'll come around and grab it. Don't worry about a quiz number. Oh, I know I'm kind of interrupting your, whoa, come back here. Your quiz writing. So we can bubble in our answers for people at home. Said B and D there. And then 2, we have C and D. Why is magnesium by itself wrong?
Because it's not a liquid.
It says liquid phase. What is the elemental state of magnesium? Solid. How do you know it's a solid? It's black on the periodic table. Oxygen. That's oxygen by itself, and oxygen is diatomic. O2, that's fantastic. Why is that wrong? It says solid. What's the elemental state for oxygen? It's in its gas state. How do you know it's a gas? Our periodic table shows it in red. Bromine. Br2, again, diatomic. Good call, except what's the phase? Liquid. What's our elemental periodic table tell us? Bromine is a liquid in its elemental state. D, we've got nitrogen. I'll come back to you in a second. D, nitrogen, diatomic, and what is its phase in elemental state? It's a gas. E, what's the issue with E? It's not H2. Hydrogen in its elemental state is H2. Okay, Troy? Got it? Okay. Complete balanced equation. I'm not going to have any space to do that one, so I'll just open it up on a new slide. The complete answer. Elemental sodium is in what phase? Solid. Plus elemental chlorine is Cl2, gas, goes to form sodium chloride. What phase was the sodium chloride?
Aqueous.
It was aqueous. How do you know it was aqueous? It said so. Next issue. Balance it. Is it balanced? Nope. To balance, you'd need a 2, and there's an implied 1. For those of you that were here at the beginning of class, or before class started, somebody asked for the answer. What answer did I say? 2, 1, 2. There it is. I said 2, 1, 2. Okay, so balancing chemical equations, we have to have the same number of atoms on both sides of the arrow. Okay, we can change the arrangement of those atoms, and that's what makes it a chemical reaction. Okay, we are moving on now, so if we could get a little bit quiet, that would be nice. We need to make sure our atoms count on the same side for both sides of this reaction. When we went through and talked about this on Tuesday, we went through and looked at balancing both total atoms. So we did sodium, hydrogen, carbon, and oxygen on both sides of the equation. And we also looked at potentially balancing it based on the complex ions. The reason we could do the complex ions is because when we look at the complex ion, what happened to it across the reaction? Nothing happened. So I can balance that whole thing as a unit across the equation. What happens if that formula changes? Can I balance it as a unit? No, because it changed. I would have to break it into the individual atoms. So when you go through and balance, be aware we've got two methods to going through and balancing. We can balance based on just the atoms themselves, or we can shift into the complex ions and balance those out. Okay? Depends on what problem you're working with. Some problems, it's easier to balance with the complex ion. Some problems, it's better to balance with the atoms. Okay? We're not going to go through and balance this one or go through the math on it because it's already balanced. Okay? The numbers in front were 1. Common multiple choice question, okay? Because it's hard to ask a multiple choice question with balancing a whole reaction. So one of the most common ways to ask this would be, what is the, or here, let me write it out, so you got that access. What is the sum of the coefficients? That's not how you spell coefficient. I was erasing. I think I knew how to spell it. Maybe. Is that right? See? I knew how to spell it. I have some faith in my spelling abilities. What is the sum of the coefficients in balanced equation? What do you have to do to figure that out? Adding was true. That's valid. What we'd have to go through and do is look at the coefficient, the number in front of each of these things. I don't see any numbers there. So it is balanced, but what's the answer? If there's no numbers there, how do we add them? If we wrote the equation and I write out H2, by definition, there has to be at least 1. So if I write out the symbol, I don't need to write the 1 coefficient because I've already specified that it's there. Okay? What happens if I need more than 1? Then I can specify my number. So the answer in this case, even though we don't see numbers in front, the numbers in front are actually implied 1s. So what's the answer for this problem? 4. Okay? Because the sum of all of our coefficients, 1 plus 1 plus 1 plus 1, gets us 4. Okay? So it's a very common multiple choice question. I typically don't like it because of the whole coefficients thing. That word tends to confuse people. That's why we're talking about it right now. Okay? Questions about that question? How else could we ask another multiple choice question? What is the coefficient in front of sodium acetate? 1. This one would be a bit trivial. You didn't even have to know what sodium acetate was. It has to be 1. Okay? So we can ask parts of it. We could also ask the whole thing. It could also be a short answer where I want you to give me your whole balanced equation. Okay? All sorts of different ways to ask these questions. All right? So when we go through and balance, what we're doing is putting a whole number coefficient in front of each substance. That coefficient multiplies everything that follows it okay, up to an operation. So let's cross and get it to resume recording. I don't want to look at this or any of all this or this. Okay, so now we're no longer looking at a balanced equation. We're just looking at acetic acid. And I want you to be able to manipulate what a coefficient in front means. If I put a 2 there, okay, how many acetate ions are in that complex? What's the acetate ion? Okay. There is 1 in acetic acid. If I have 2 molecules, the 2 applies to that. Okay? Hopefully that one was fairly straightforward. Let's make it trickier. How many oxygens are there? The 2 applies to everything in front, including the oxygen. There are 2 oxygens in 1 unit. I have 2 units. 2 times 2, 4. Last one, probably the trickiest of them. How many hydrogens are there?
7.
How many different numbers are we going to stick with? The 2 applies forward to that hydrogen, and it also applies forward to that hydrogen. We have 2 hydrogens there, and we have 6 there. Our total comes out to 8. Okay? So be careful with what those coefficients mean, okay? Because it can haunt you later if you aren't very careful with those. The coefficients will always be put out in front. We will never, ever touch the coefficients in a formula. Okay, why? If you change the formula, you're not working with that compound anymore. You've changed to a new compound. Okay? Balancing says, here's our equation. Make sure everything balances out. Don't go through and change the reaction. Okay? Just balance the atoms by changing the coefficients. How many of those molecules are necessary to do the reaction? Okay? Kind of makes sense? Okay. So, guidelines for balancing reactions. Pretty similar to what the textbook has. I don't think I've done anything too far outside of what they've got organized. So, to start off with all balancing reactions, predict the products if necessary. You will have to predict what products are possible in a reaction. Okay? But there's only certain reactions that will make you predict those products. Okay? So at this point, we don't have to worry about it yet because we haven't gotten into those different reaction types. Okay? When you predict the products, one of the things that you have to make sure that you've accounted for is now step number 2, which is make sure your formulas are correct. How do you make sure your formula is correct? What's balanced? You're right. Whoever said balance.
Formula, like everything, make sure everything on one side is good, has everything on the other side.
That's balancing the equation. So we got to be careful. You can't balance the equation yet. We have to make sure our formula is balanced. How do we balance the formula? What are we trying to balance out? The charge. So when we looked at sodium acetate, sodium ion has what charge? +1. The acetate ion has what charge? -1. So when we looked, oh man, I'm going to regret this, but I'm going to do it. Oh, cool, wasn't that far back. When we looked at our product, we would first evaluate and say, is that formula balanced? Is it correct? Yeah, the charge balances out. I have a 0 charge. What happens if we had, say, a different formula? Let's say instead we reacted, I'm not going to do a new reaction. Let's say we had potassium and sulfate. We have to make sure our formula is balanced before we start the equation. If we just write KSO4, is our formula balanced? No, why not? Potassium's +1, sulfate is -2. So you remember all those nomenclature rules where I said you need to memorize all of the ions and their charges? Why? Because you need that to be able to go through and balance equations. If you don't know that material yet, you're not going to pick up and be able to balance equations. Okay? So you will be constantly reviewing that stuff to go through and balance. If you've got problems with it, now is a good time to keep going back and practicing. If we're going to make potassium sulfate, it has to be K2SO4. Why can I change the number in the formula now? Because I'm balancing the formula. I'm balancing the charge. I'm allowed to do that because what I'm doing is looking only at the formula. Now that I have the correct formula, now I can't touch it. The only thing I could adjust would be the number in front. Okay? Which would be looking at rule number 3. So we would now go through and begin to balance our equation, starting with any atom other than hydrogen and oxygen. Okay? This rule is not critical at this stage. If you have to move further into general chemistry, particularly second semester, that rule changes, or not, doesn't change, but it becomes much more relevant. When you go through to balance, you balance any atom other than hydrogen and oxygen. Later on, you would then go back and balance hydrogen first, then oxygen. Okay? Again, you don't need to know that. If you continue to read chapter 17 beyond the 3 sections that you're responsible for, 1, 2, and 3, you'll run into that issue. Okay? Next, yes? It has to do with how you balance out hydrogen and oxygen. In some equations, you balance it out by adding another atom or another molecule. Okay. Rule number 4. Place whole number coefficients in front of formulas to increase the amount of atoms that follow that follow up to that operation. Okay? So that's what we did by putting in 1s or 2s. We always put it in front of the formula, and that number applies to everything up to the operation. We can then move through to the next atom or the next polyatomic ion. So we keep repeating steps 3 and 4 until we've verified all of our atoms, which is what we did with the first example up on the whiteboard with our hydrogen, or hydrogen and oxygen making water. Okay? Then what do? You check your work. You go back to the very first atom and you check it. Okay? Is it still balanced? Okay, if it is, what do? Move to the next atom on your list. Is it still balanced? If it is, move to the next one. If you have to go back and now change one of the numbers, you now have to check and recheck your work. You need to be able to go through and compare both sides of your equation for the number of atoms, and it needs to be the same for every single atom. You cannot change a number. If you have to go back and change a number, you must recheck your work. Okay? So, issues that students typically don't like with this. There's a lot of rechecking. Okay? There's a reason you recheck it. What happens to your answer if you recheck it? You get it right. If you don't recheck it, you get it wrong. Recheck your work. Okay? Balancing equations takes a little bit of practice to get used to, but once you've got the patterns down, you should be able to check and recheck your work very, very swiftly and start to see where things become problematic and you don't have to recheck as much. At this stage, you should be rechecking 2 or 3 times. Okay? Once you've checked it 2 or 3 times, check it again. Okay? Then check your formulas. Make sure your formulas are balanced. If at any point during that phase you have a question about whether your answer is correct, go back to the rules, go back to nomenclature, check it again. Once you've checked it an infinite amount of times and you are now 100% positive you are correct, then and only then should you check the answer. If you check at any point before that, you have defeated the purpose of that problem. You need to do an entirely new problem. Okay? Cannot stress that enough. Your answers are hurting you. Do not look at the answer until you are positive you are right. Okay? Positive, 100%. If you get the answer wrong, that problem is invalid. You have to do a new problem. Okay? Cannot stress that enough. The very last step that we'll do is verify that we use the whole, or the smallest whole numbers possible. Okay? They have to be the smallest, otherwise what we've done is scaled the reaction up, and we're not allowed to do that, at least at this stage. So you have to make sure that you're using the smallest numbers possible. It's easy to make that mistake in certain circumstances when you go through and balance, so it can be helpful that after you've balanced everything, you go back through and now decide, did I use the smallest whole number possible? Okay? Questions about any of those steps? Okay. Since we already did that first one, somebody who was here for that, want to tell me what your answer was? 1. Whoops, I did that wrong. Wow, that was 212 again. Yeah, it was. 212, the sum of our coefficients. We have 5. Next equation. Okay, this one I intentionally already started to balance. Okay, this is to cover Rule 7. So we could go through and check each of these first. How many hydrogens do we have on the left-hand side? The 2 applies there and there. We get 4 hydrogens. Right-hand side. The 4 applies forward. We get 4 hydrogens. Hydrogens are balanced. We can now check our bromine. How many bromines do we have? End up with 4 again. On the right-hand side, our 4 applies forward as well, and we get 4 bromines. Everything is balanced. Our last step was verify that we use the smallest whole number possible. Did we in this case? So now what we would go back through and do is look at our whole number coefficients and decide, did I use the smallest number possible? No. I can go through and divide everything by 2. So the answer is going to be H2 gas plus Br2 gas goes to 2 HBr gas. Okay? What's your whole number coefficient answer? 4. On a test, what I might do is give you 2H2 plus 2Br2 plus 4HBr. Say balance the equation and give me the smallest whole number coefficient. What do you think one of the other answers is going to be? 8. Why 8? Because you went through, looked at it, and said, yep, everything was balanced, and just added everything up without doing the last step. Okay? Questions about that one? Okay? So I did 2 really easy ones. Lucky for you, you now get to do 2 really hard ones. So go ahead and take a stab at these 2. I'll again give you 3 minutes to go through and work on these. If you've got questions, raise your hand. Talk to the people around you that you would be expected to predict the products on.
Right.
Okay? Not yet, because we haven't talked about that reaction, but you are expected to be able to do that one. Okay? So to start off, I would start with our aluminum. Aluminum on the left-hand side, I see 2. Right-hand side, I see 1. So I need to make that 2. Putting a 2 in there. Now I'd move to, in this case, since we don't have hydrogen or oxygen really to balance, at least the way I've got it set up, why do we not have hydrogen or oxygen to balance? I'm balancing them as the polyatomic ion. So I don't have to wait to balance oxygen at the end. Okay? The reason I can balance the polyatomic ion is because it didn't change. So SO4 on our left-hand side, we've got 3. On the right-hand side, how many do we have? 1. That needs to become 3. How do I do that? 3 in front. Barium. How many bariums do we have on the left-hand side? We only have 1 barium currently. On the right-hand side, we have 3. How do we know we have 3? Because when we went through and balanced our sulfate, it applies forward. All right? That doesn't balance. I need to make the 1 barium on the left equal to 3. How do I do that? 3 in front of the barium. Now I've got the nitrate to go through and balance. How many nitrates do I have? On the left, I have 2 and the 3. There are 6 nitrates. On the right-hand side, how many do we have? Oops. We've got the 3 and the 2. We've got 6. So we've now gone all the way through. We need to go back through and evaluate and check. How many aluminums on the left-hand side? 2 on the right-hand side. 2 sulfates on the left. 3 sulfates on the right. 3 bariums on the left. 3 bariums on the right. Nitrates on the right. Nitrates on the left. 6. What does that mean? It's balanced. You're now, well, almost done. Now you'd have to go through and make sure you answer the question that was asked. If I asked you to provide the sum of the coefficients, 1 and 3 is 4, plus 2, 6, 7, 8, 9. And our answer would be 9. What if I just asked for the coefficient on barium sulfate? 3. So with this question in a multiple choice, I can guarantee you're going to have a bunch of different answers there. Those answers will be 1, 2, 3, and 9. And goats, because I ran out of options. Why put all 4 of those answers there? Because they're all valid answers to different questions. Make sure you answer the question that's asked. Okay? How can you ensure that you're answering the correct question or you're answering the question that's asked? Good idea to either highlight or underline what the question is asking. Okay? Still can't tell you how many different exams I'm seeing where the multiple choice section is blank. You're right, you don't get graded for that work, but think about how many questions you're looking at. For that last exam, you had roughly 40 multiple choice questions. By the end of that exam, you saw 160, I think I did that math actually wrong, it's more than that, 160 wrong answers and only 40 correct answers. If you don't write anything down, all you see by the end of the exam is wrong answers, which means if you're jumping around through the exam, the likelihood that you answer the correct one is going to be wrong. Okay? So put some information down so you don't have to think about it. Last one. We're going to go through and balance that. Last one, can we balance based on polyatomic ions? Because I do see that I need to erase the nitrate. I do see the polyatomic ion carbonate on the left. Does it show up on the right? No. So I can't balance based on the polyatomic ion method. I have to go through and balance by atoms. What atom would we start with? Remember, ultimately, it doesn't matter unless you have to push into further chemistry. If you're pushing into further chemistry, you should balance with the carbon first. How many carbons do we have? And 1. We could then go through and balance our hydrogens. How many hydrogens do we have? 2. Whoa. Hydrogens here. 2. Oxygens. 3. And why is it 3? I only see 2 in CO2. You also have the water you have to account for. You're totaling all the atoms possible. Okay? So what's your answer for this one? It's now balanced. What's the sum of your coefficients? 3. Okay? Questions about balancing? Yes?
So the aqueous means it's dissolved in water?
Yes.
In water? Why
Yes.
don't we add in H2O for aqueous?
So the reason we don't add H2O in for aqueous is then it looks like we're reacting carbonic acid with water. We're not. We're taking carbonic acid in water, dissolved in water. That molecule itself decomposes into CO2 and more water. If we write in water over here, we're now saying water is reacting with this. It's not. In this case, the carbonic acid destroys itself. Can you put,
It just
I mean-
makes me heartburn when I think about the fact that it's in water, so you got more hydrogen and oxygen technically. Like,
true, you do have more hydrogens and oxygens if we do it in water. But what happens to each and every one of those water molecules? It does not change. So yeah, I may have 50 million water molecules at the beginning, but what do I end up with at the end? 50 million again, plus a little bit extra from the carbonic acid decomposition. All I care about is that little extra. The rest of it didn't change. It's a steady state. Okay? Other questions? Okay, if I remember correctly, we're now going to start looking at classifying your chemical reactions. Each of these, we're going to introduce some different types of reactions, look at the names or the words to describe the reaction, try and write it out into an equation, and then try and balance them. So we've got these 5 common chemical reactions. There is a 6th which kind of floats along these. Each of these can be classified according to that 6th potentially or not. We'll look at that 6th one towards the very end. Okay? So these are your 5 chemical reactions. You'll notice that what I've supplied are general formats for each of these. So that when you look at a reaction, you should be able to say, that's a combination reaction. That's a decomposition. That's a single replacement. Okay? I know you just looked at this, but I'm going to be mean because now I'm going to shift it away. Last reaction. What happened to it? We started with 1 molecule and we became 2. We decomposed it. We took it apart. Decomposition. What happened with our first 2 reactions? We started with 2 and we ended with 1. We're looking at combining. Combination reaction. Probably the trickiest one for you guys to see currently would be that last one, or the middle one. Okay. Aluminum is what charge? Positive. So it's also known as a cation. Sulfate has what charge? Negative charge. So it's known as anion. Barium's a positive. Cation. Nitrate. Anion. What happened as we went through the reaction? What was partnered up with the aluminum on the left-hand side? Sulfate. On the right-hand side? Nitrate. Where did the nitrate come from? The other molecule. What's paired up with the barium on the left-hand side? Nitrate. What's it paired up with on the product? Sulfate. So what did we do? We swapped individual ions. How many times did we swap? We swapped twice. We're looking at a double replacement. Okay? So all of the symbols can get very confusing to kind of separate out when we look at larger, more complex reactions. That's what this formatting is supposed to do. Show you kind of the breakdown within it. You'll notice we don't see any coefficients and we don't see any subscripts. Those can change for every one of these types of reactions. The reason they aren't included is it doesn't change the type of reaction. Okay? What will it change? Our coefficients and our subscripts. It'll change what our products are. Okay? As far as which of these reactions you need to be able to predict, single replacement, double replacement, and neutralizations. Those 3 I fully expect you to be able to predict products on. Okay? And we will talk about the rules on predicting those. Some of them are easier than others. For instance, the neutralization. Okay? In a neutralization, it's also known as an acid-base reaction. What's a characteristic of an acid? Hydrogen. So it starts with hydrogen in one of the molecules. We haven't talked about our base definition, but our simplest base definition is the presence of hydroxide, OH-. So what we can look for a neutralization reaction is on the reactants, do we have a hydrogen and OH? Yes. What type of reaction did we do? Neutralization. Okay. Officially, yeah, aqueous. I pulled the phase information too from it because it's not as important. And the process of that reaction, hydrogen and the hydroxide combine to form water every single time. What else is left? Our ions. Why in the neutralization reaction did I write Ba and not Ab? We always start with our cation. Okay, so it just happened to be how I organized it to begin with. Our B is going to be our cation, A is our anion. How would we know that? What charge is on a hydrogen ion? Which means the A has to be what charge? Negative. Otherwise, they repel away. What charge is on the hydroxide ion? Negative. What charge does the B have to be? Positive. Okay. So, any questions about the general formats that you're seeing here? Yes.
You're going off ions here, what about covalent stuff?
Covalent stuff you see up in the combination and decomposition reactions. And for those, the predicting ability becomes a lot more difficult. That's ultimately organic chemistry. Yep. So thankfully, you don't have to worry about that. At this point, what you have to worry about are your ionic compounds and your acids and bases. Okay? So be happy. We don't have to do all the predictions. Okay? Questions about, again, formats? Okay. Look at 3 reactions. Okay? There's 3 of these types of reactions. We're going to try and figure out what these are. Those 3 possible types are the reaction of a metal with oxygen, the reaction of a nonmetal with oxygen, and the reaction of a metal and a nonmetal. Okay, so let's look at our first reaction. Magnesium metal reacts with oxygen gas to produce magnesium oxide. How do you know magnesium oxide? So what we can do is go through and start. Magnesium plus our oxygen goes to, those are the only things we've got. We've got to put magnesium with oxygen, right? What type of reaction would this be? Combination. Should we start balancing yet? Let's change that phrasing. Should we start balancing the reaction yet? No, why not? We have to balance each of the formulas first. Okay, and we'll have to specify our phases. Magnesium. What happens with magnesium in its elemental state? What are we looking at? It's a solid. How many magnesiums are there? Just 1 as far as we're concerned with magnesium. Why is it not 2? It's not one of those 7 that you had to memorize. Okay? Oxygen. It's a gas, so we could specify our phase. But it's a diatomic molecule. It must be O2. Move to magnesium oxide, our product now. What's the charge on a magnesium atom in that kind of a compound? Why is it +2? We're looking at an ionic bond. How do we know it's ionic? Metal and a nonmetal. What's the charge on oxygen? -2. Do our charges balance? Yes. Now that we've got each of our formulas correct, now we can balance the equation. Oh, whoops. And the phase, I wouldn't expect you to, this is actually a type of reaction I don't expect you to be able to predict, but I figured I'd see what you guys could do with it. It does come out as a solid in this case. Again, I wouldn't expect you to know that. Okay? Now we can balance the equation. How do we balance the equation? Coefficients. How many magnesiums do we have on each side? 1 and 1. Is that balanced? Yes. How about oxygen? 2 on the left, 1 on the right. How do we balance? Nice catch. We need 2 oxygens on the right-hand side. How do we do that? 2 in front. Resist the temptation to say you're now done. Go back and check your work. How many magnesiums do we have on the left? How many magnesiums do we have on the right? 2. Is that balanced? Nope. What do we have to do? 2 in front of our magnesium on the left. Check our oxygens. What's our oxygen now at? 2 and 2. Since we went back and changed a number, what does that mean we have to do? Go back and check again. Magnesium. How many magnesiums do we have? 2 and 2. Oxygens. 2 and 2. We went through it and nothing changed. Because we're prone to make mistakes, let's go back and check it again. How many magnesiums do we have? 2. How many on the right side? 2. How many on the right side for oxygen? How many on the left side? 2. Is it balanced? Yes. Is this equation correct? Yes. We've balanced it. We accounted for all of our phases. Everything is correct. We can now advance forward. Okay? A lot of you, I could tell, were frustrated with the go back and recheck. Go back and recheck. Okay? Be frustrated now. Get the answer right. Make me happy and you happy when you get better exam scores. Mark.
So as far as the test setting goes, will we have enough time to do that many checks for one problem?
You tell me. When you left the last exam, how much time did you leave on the clock? Yeah. So at this point, you have lots and lots of time. I will still be pushing the exam to be long. In fact, I will make it longer because your final exam is even longer, okay, than what we've seen already. So I want you to be pressured when it comes to the in-class exams so that you can rock the final exam. Okay? Why? The final exam is worth more points, and It's doubly important because it could replace your lowest exam score. Okay? I want you going into the final exam ridiculously happy and ready to go. Yes?
What if you don't know what to label it?
What do you mean label it?
No.
The phases? So in this case, this is one of the reactions you're not expected to have memorized, or sorry, be able to predict products on. I went through and did it here because with those two atoms, you could predict the formula. You wouldn't be able to predict the phase. Okay? You wouldn't be asked this question in this way. Okay? The other way that we could look at this is first off, well, now that I've given you the answer, what type of reaction did we just do? Combination. We took two pieces and made it one piece. Okay? So we took magnesium as A, oxygen as B, and we put them together to make our new compound. Okay? So what we evaluated was a combination reaction. There's a reason I said you didn't have to have those or be able to predict those products, because you don't know that phase information. You should be able to predict what formula. The phase is questionable.
The only thing I think I'm confused on is on the last one that we did, we wrote the two for the end product, we wrote the two in the very front. Instead
Yes.
of putting the subscript T in that.
The subscript changes what? What does the subscript change? The formula. When you balance an equation, can you change the formula? No. Once you're going through to balance the your equation, you can only put in coefficients. You cannot put in subscripts. Okay? And you can ask again after class. We can go through it a little bit slower. New question. Again, we got these kind of color-coded. This one, you'll notice I've given you some more information. Sulfur solid reacts with oxygen gas to produce sulfur dioxide. What's our standard state for sulfur? Solid plus oxygen gas. How do we specify it's a gas? What other information do we need to add to that? Oxygen is diatomic, goes to produce. Sorry. SO2. How did you know it was SO2? You were good with your nomenclature. You have to understand your nomenclature to be able to predict what these products are. You'll notice with this one that I didn't even think to ask what the product was or have you try and determine the product. Why? What type of bond do we have in the product? Between a nonmetal and a nonmetal, that is a covalent bond. You will not be expected to predict covalent bonds. Okay? So we now have the individual pieces. We now need to go through and balance. Is it balanced? No. How quick can you do it? We now have it balanced. Did I do that right? Oh, no, I didn't do that. That's all ones. Why did I can add, trust me. Believe me. Let's try that again because I goofed that. If I make the mistake, I guess I got to repeat it. How many sulfurs do we have on each side? I count 1 and 1. It was my fault, so I'll go through and do it. Oxygens, we have 2 oxygens. And oxygens, we have 2 oxygens, which means go back and recheck our work. Sulfur, I see 1 and 1. Oxygen, I see 2 and 2. And because I goofed the first time, sulfur, 1 and 1. Oxygen, 2 and 2, which means everything is balanced. What's the sum of my coefficients? 3. 1, 1, and 1. Okay? Questions about that one? Last combination reaction is looking at the reaction of a metal and a nonmetal. This is, again, one that you should be able to predict the formula on. Again, I wouldn't expect you to be able to predict the phase. Why should you be able to predict the formula? What type of bond do we make when we make a metal and non-metal combination reaction? We make an ionic bond. Should you be able to predict the formula of an ionic bond? Yes, because you know the charges for each of those individual species. Okay? So I'm just going to try and go through this one as fast as I can. In theory, not screwing it up like I did the last one. Lithium in its standard state is a solid. Bromine is a diatomic molecule, a gas, goes to produce our metal and nonmetal. Charge on bromine is -1, charge on lithium is +1. Charge is balanced, my formula is correct. Most ionic compounds are solids, so I'll just add that information just for your sake. Okay. This is, again, remember, with these types of reactions, I don't expect you to be able to predict the phase. Okay? Is it balanced? No. I've got 2 bromines on the left and 1 on the right. I need to put a 2 and 2. Hey, I got my 2, 1, 2 back. And my total comes out as 5. Okay? Questions about the combination reactions? Yes?
Are we looking at their charges because it's a metal and a non-metal?
We're looking at the charges to balance our formula because it's an ionic bond. So we had to make sure our formula was correct before we could go in and balance the coefficients.
So we only check that on the formula, not on
These formulas must be correct too. Your formula must be correct on both sides of the equation. If we look at elemental lithium, how many atoms are there? It's just Li. It's not one of the diatomic elements. If we look at bromine, bromine is diatomic. It has to be Br2. Okay? So we are checking the formulas on both sides of the equation. Okay? Other questions on the combination? Heating solid mercury oxide produces mercury metal and oxygen gas. Let's do the equation on this one, at least get this first equation down, and then we'll end there. Starting off with, what do we have? Mercury is Hd, and we have oxygen. It says mercury 2 oxide. So the charge on mercury is charge on oxide. What's the phase? How do you know it's a solid? It says solid, just checking. So we've got our formula. It says that we heated it. How do we specify that we heated it? Delta symbol over our reaction arrow. Produces mercury metal. Mercury is a freaking weird one, but let's just run simple. Hg solid plus, oh, good call, thank you. How do you know it's a liquid? The blue on our periodic table produces mercury metal and oxygen gas. What is our formula for oxygen gas? O2 with our gas. We've now balanced each of our independent formulas. We can now go back through and balance our equation. Is the equation balanced? No. What do we have to do? Mercury is balanced already, 1 and 1, so we could move to oxygen. It's 1 and 2. How do we fix that? We need 2 oxygens on the left. Now our oxygens are balanced. Are our mercuries balanced? Nope. How do we fix our mercuries? Out of 2. What type of reaction did we do? Decomposition. We started with 1 and broke it into 2. Where's my, move forward. We've got our decomposition reaction. With these examples, I know you guys want to leave and that's fine, you can keep packing up. With these examples,